Welcome everybody. Today we're doing lesson 7.2, scientific notation. Alright, so scientific notation is really just a way to write really big or really small numbers. And we use that with this little a times 10 to the n. So everything is times 10 to some power. So we've been dealing a couple days with exponents and base 10, and now we're getting into some scientific. So not everything is going to start with a 1 necessarily. Alright, so this first example, Jupiter's orbital speed is 1.10 or 1.3 times 10 to the 4th meters per second. We want to figure out how fast is Jupiter moving in standard motion. So 1.3 times 10 to the 4th, that's 1.3 times, now 10 to the 4th, we could write as 10,000. 10 times 10 times 10 times 10. Alright, so if we do 1.3 times 10,000, we get 13,000. Alright, so that's written in standard form. Alright, we don't want to forget our label, meters per second. Alright. Another thing you might notice is we raised it to the 4th power. Our decimal moved 4 places. Right, we were at 1.3. 1, 2, 3. Moved it 4 places to get 13,000. So let's do a couple examples. So we want to order these from least to greatest. So first, I'm going to turn them all into a decimal. Right, so 6.9 times 10 to the 4th. That's going to be a 6. Oops. Then there are going to be 4 digits after the 6. All right, the remainder of that decimal, so in this case it's the 9, and I fill the rest with zeros. All right, so 5 times 10 to the 4th is going to be a 5 followed by 4 zeros, because I'm raising it to the 4th power. 5 times 10 to the 5th would be 5 with 5 zeros. And now 6.9 to the times 10 to the 5th is going to be a 6. And there are going to be 5 digits after the 6. So a 9 and 1, 2, 3, 4 zeros. Alright, so all of these have our first digit. And then whatever our exponent was, that's how many digits there were after. So 4th power, 4 digits. 4th power, 4 digits. 5th power, 5 digits. 5th power, 5 digits. So that's kind of our shortcut. So if I want to go least to greatest, that's going to be the, let's change colors. 5 times 10 to the 4th is the smallest. Then 6.9 times 10 to the 4th. Then we have 5 times 10 to the 5th, followed by 6.9 times 10 to the 5th. Alright, so the reason we can tell these are from least to greatest is just by looking at them. We know 50,000 is less than 69,000. And we know both of those are less than 500,000, which are both less than 690,000. Alright, now what we can do is we can figure out least to greatest just by looking at the base and the exponent. Alright, so a couple things we notice. Smaller exponents have smaller values. Alright, but what if we have the same exponent? It's like a 4 and a 4. Well, if you have the same exponent, then, so if same exponent, then the smaller base value is smaller. So that's if you look at the first two, 5 times 10 to the fourth and 6.9 times 10 to the fourth, both have 10 to the fourth, so they have the same exponents. So we look at the smaller base. Well, 5 is smaller than 6.9, so 5 times 10 to the fourth has to be smaller than 6.9 times 10 to the fourth. All right, so if we recall with negative exponents, all right, that's the inverse. All right, so we can take our little trick of moving the decimal and do it the same thing, except instead of moving the decimal to the right to make the numbers bigger, we are moving the decimal to the left to make the numbers very, very small. All right, so this first one, 1.3 times 10 to the negative fourth. So what I'm going to do is start with 1.3, and I need to take this decimal and move it 4 places to the left because it's a negative 4. So 1, 2, 3, 4. All right, then any space I need to fill with a 0. What I mean by space are these little trough things. All right. So our final answer, we get 0.00013. All right, so we had the decimal at 1.3 and moved it 4 spaces to the left to get 0.00013. All right, so you might be wondering, why can we use the shortcut of just moving the decimal? Well, our number system is base 10. And so what that really means is we count, and we get up to 10, and then we kind of start over. 11, 12, we get the teens, then the 20s, then the 30s, 40s, 50s, 60s, all the way up to 100s. All right, 100s are just still base 10. Then multiply that by 10, you get 1,000. Multiply it by 10, you get 10,000 and 100,000. All right, so each decimal place is like think of it like a base 10 or a tens place, tens position. So every time you're moving the decimal 1, you're moving it by a power of 10. All right, so that's why in scientific notation it's always times 10 to some exponent. All right, so if we take our first example here for ordering least to greatest, 3.2 times 10 to the negative 6. So again, if I start with 3.2, move my decimal from right there, I need to move it 6 places. 1, 2, 3, 4, 5, 6. That gives me 0.0000032. All right, so there are 6 digit spaces until that 3. So if I have 3.2 times 10 to the negative 8th, that means I need to move my decimal 8 spaces to the left. So 0.000000032. So if we move on now, so moving on to 5.4 times 10 to the negative 6. I'm going to start with 5.4, and I know I need to move my decimal 6 spaces to the left, again because negative 6. All right, and then fill all of those empty spaces with zeros. So 0.000054. All right, and the last one, 1.2 times 10 to the negative first. All right, so remember, if I start with 1.2 and I move my decimal 1 space to the left, that's ending me up at 0.12. All right, another way to think of this is 1.2 times 1 over 10. All right, so really we have 1.2 divided by 10. And again, we could have gone back and said this is 5.4 times 1 over 10 to the 6th. which is 5.4 divided by 1,000,000, so divided by 10 to the 6th. That's why we're getting very, very small numbers. All right, so if I want to order these from least to greatest, I want to look for the smallest number first. All right, so that's going to be 3.2 times 10 to the negative 8th. From there, the next smallest value, we have 3.2 times 10 to the negative 6. 0.000003 is less than 0.000005. So our third one then, we have 5.4 times 10 to the negative 6th, followed by 1.2 times 10 to the negative 1st. So what you might notice here is, again, the smaller exponents create the smaller values. All right, just be careful, because remember, negative 8 is smaller than negative 6, even though the 8 looks bigger. All right, if you have the same exponent, so like here we had a 3.2 times 10 to the 6th, or negative 6th, and 5.4 times 10 to the negative 6th. In order to tell the difference between those two, you want to look at the base, that first number. So 3.2 is less than 5.4. So 3.2 times 10 to the negative 6 is less than 5.4 times 10 to the negative 6. All right, so for our last one, we are turning this time, careful, because we're switching it up. We are going greatest to least first. All right, and we are not turning these into decimals. So if I'm going greatest first, I want to look for my biggest exponent. So I have 3, negative 3, 3, negative 5, and 6. All right, so that 6 is my biggest exponent, so that's going to go first. 5.9 times 10 to the 6th. Let's cross it off. All right, now I have exponents of 3, negative 3, and negative 5. Well, the 3's are bigger, so that means I need to determine between 4.5 times 10 to the 3rd, 7.2 times 10 to the 3rd, which one is bigger? Well, with the same exponents then, we need to look at that first value. So 7.2 is greater than 4.5, so 7.2 times 10 to the 3rd is greater than 4.5 times 10 to the 3rd. All right, now moving on, I just want to keep looking at my exponents. So negative 3 is bigger than negative 5. So 4.5 times 10 to the negative 3rd is smaller than 6.8 times 10 to the negative 5th. All right, so you can see that our exponents going from greatest to least, the exponents go from highest to lowest. All right, so remember the shortcut. If you have a positive exponent, you're moving the decimal that many spaces to the right. If you have a negative exponent, you're moving the decimal that many spaces to the left. Good job today.